Thanks, Paolo.
Okay, I think we're ready to start again. So we have Richie Yeung, who's going to talk about completeness for arbitrary finite dimensions of ZXW calculus.
Is this recording?
This is recording, yes. Do you want not to be recording?
No, it's okay. As long as it's recorded, that's all good.
Yes, this should be recording. Let me double check.
That's last time we forgot to record.
Yeah, it's recording. All right.
Okay.
And please take it away. And please, if the people online can tell us in case the sound is not good, let us know. All right, please go ahead.
Okay, thank you. Hi, everyone. Today I'm talking about the completeness of ZXW calculus for arbitrary finite dimensions. This is joint work with, let me start my timer, sorry. This is joint work with Bodajar, Hani, Razin, Leah, and Bob. So this is the rough outline of the talk. I'm going to first introduce the ZXW calculus, and then I'm going to introduce its generalizations to qubits, and then I'm going to talk about completeness, which is the main thing we did in this work. So
Let's also all right.
Hit that. And that. Yeah, great. So before I get into it, can I have a show of hands to see how many people have heard of the ZX calculus? Okay, cool. So I'm gonna keep it brief. So ZX calculus is a graphical calculus for doing reasoning with quantum computing, and specifically you can use it for quantum circuit compilation. You can do the quantum circuit simulation with it, error correction, a lot of things. And here's another example. You can do measurement-based quantum computing. You can phrase these protocols using the ZX calculus. Yeah, thank you. And the generators consist of these Z and X spiders, which are Frobenius algebras, and they satisfy this bialgebra and Hopf laws because they're mutually unbiased observables. On the other hand, there's this other slightly less well-known calculus called the ZW calculus, which uses the Z spider and the W spider, which are basically the two like free qubit maximally entangled quantum states up to local conjugation. And that forms a calculus as well. And it has slightly different properties. It's very good for handling sums, which the ZX calculus is a bit less good at. And it's actually very naturally amenable for linear optimal quantum computing. So that's another thing it's used for. So if you took the ZX calculus and the ZW calculus and you combined it into a single calculus, you're going to get something called the ZXW calculus. And it has the advantage of ZX calculus where it's very easy to do these rewriting rules, but you can also encode lots of problems in it that previously it's not easy to encode in the ZX calculus, such as Hamiltonian simulation. You can phrase quantum machine learning problems in it. So you had an arbitrary ZX diagram. To differentiate that diagram with respect to a specific parameter theta, you can just add this W spider and then connect it to all the spiders with that parameter in it. So that's how you do differentiation in ZX calculus. But here we're going to talk about the qubit generalization of the ZXW calculus, which is also new in this paper. So what is a qubit, right? So a qubit, first of all, you can express these quantum states as a superposition of the basis states 0 and 1. And alpha and beta are complex numbers such that their magnitudes sum up to 1. Qubits are like a high dimensional generalization of that. So instead of having two computational basis states, you have D of them. And then these AIs have to square and sum up to 1. So your quantum state can be, one qubit can be a superposition of all D of these states. So that's a good thing to do if your quantum system, the quantum PC you're building uses quantum physics where there's already naturally multiple levels of quantum states. So that's the reason why you want to work with qubits, because these high dimensions come for free already. And now I'm going to talk about completeness, right? So what is completeness in terms of like graphical calculi? So each of these generators that I'm going to talk about more later have a linear algebraic interpretation. They can be interpreted into vector spaces or Hilbert spaces. And so you can have these two diagrams that look different syntactically, but have the same interpretation underneath. So completeness says if these diagrams are have the same interpretation underneath, there should be a set of rewrite rules that convert one diagram to the other. So that means like practically, if I want to do like quantum circuit compilation, I'm reasoning with these quantum circuits. I can see that with completeness that all rules can be derived using this fixed set of rules. So I can always work within this calculus without expanding all the matrices out, which would be expensive. So this is a rough history of completeness. A lot of people have tried doing completeness in different forms. So Miriam Backens tried doing qubit Clifford completeness a while back. Jondel, Perdue, and Wilmot also did their own for Clifford plus T, and a bunch of people did the universal fragment. And then later on, there's more interest in these high dimensional versions of the graphical calculi. So there's also attempts there. But this work does completeness for arbitrary dimensions, for universal, for all dimensions, yeah. So this axis is kind of the dimension of the vector space you're working with, and this is the kind of algebraic kind of aspects of it. What kind of gates you have? Like, so here you can have rotations of arbitrary phases in universal. So yeah, I'm going to introduce the qubit ZXW calculus. Looks a bit different. So these pink spiders that have a single wire out, they normally denote ket 0 or ket 1. By the way, these diagrams read downwards. So kj here maps to minus j, which is a bit weird. It's an unfortunate choice, but it has some good properties later on that redeems itself. So yeah, the kj maps to d minus j instead of j. The Z spider still copies computational basis states. So this doesn't do cloning of arbitrary quantum states, which is impossible with linear maps, but it copies only the computational basis states. You have the X spider, which normally does the XOR if you plug in two of these pink spiders above. So it's a monoid. But here we generalize the XOR to be addition and modulo D, since XOR is addition modulo 2. And we have this thing called the multiplier. Those who know more about the ZX calculus will be familiar with the Hopf law of the ZX calculus, where you have an even number of edges between these green and pink spiders. You can remove an even number of them, so they can become disconnected. Here you can remove up to modulo D. So when you have D of these Ys, you can remove them. And one thing they can do is these multipliers themselves act as a multiplication on the computational basis states. Modulo D again. So you have addition and multiplication modulo D, which is good on the computational basis states, but we're not just doing arithmetic, we're doing like arbitrary quantum states where it can be superpositions of these quantum states. So yeah, we often denote these multipliers with negative numbers. It's just modulo D. So think of minus m as D minus m. And finally, we have the W of the ZXW calculus. The W node comes from the W state, but you kind of just bend it up and remove a dualizer. So it looks almost like the W state, but we generalize it to high dimensions, to D dimensions here. And when you plug in a 0 state, they're going to be disconnected. So it's going to be 0, 0. You can see that from the Dirac notation. But if you put kj in, that's going to be one of the other basis states. It's going to give you like I0 or 0i, the superposition of that. We also have the Z box. The Z spider the 2-qubit version of it looks very much like a rotation gate, a Z rotation gate, up to a global phase. So when you put in ket 0, it doesn't do anything. When you put ket 1, it multiplies it by this complex phase of e to the I alpha. But here we want to express more general things, not just phases like of unit 1, unit phases. So we're going to replace these exponentials with arbitrary complex numbers with a Z box. So instead of e to I alpha, you have A, where A is any complex number. That's for qubits. This is for qubits. And now to go from qubits to qubits, we have these spiders these Z boxes that store like a list of numbers from A1 to AD minus 1. And yeah, that's the natural generalization of the Z box. So A with the arrow here, that's a vector of numbers. And in general, these things are like spiders. They're Frobenius algebras. So you can add multiple legs, and this is a linear algebraic interpretation of it. And normally Z spiders have this fusion law. If you have like alpha and beta, you fuse them together, you get alpha plus beta. Now you're going to get, element-wise multiplication because there's not each side. Like, you're multiplying the phases together and to get addition at the top. And now you're just multiplying the complex state numbers directly. That's going to be useful later. There's the bioalgebra rule. Because remember the green spiders act as copying on the computational basis states, and these pink things represent XOR, or now addition modulo D. So if you copy everything and then add them pairwise, that's the same thing as if you just added everything once and then did multiple copies of it, right? So this is the bioalgebra rule. This makes a lot of sense on computational basis states. We have a slightly different version of it. First of all, we have a bioalgebra between the W and the Z as well. So imagine, it's not here, but like imagine there's one where there's a W spider here and a single Z spider here. That's the bioalgebra for Z and W. But there's also a trialgebra rule where it turns out you can replace one of these W spiders with a pink spider, X spider. And the reason for that is we're working with the one particle subspace. We've projected into subspace where W and XOR actually behave exactly the same way when you only reason with a single particle. And the trialgebra rule generalizes to multiple spiders. So if you had a normal kind of bioalgebra setup where everything is connected to everything in this kind of this kind of way, you can replace all but one of these W spiders with an X spider for the reasons I already explained. And when you put everything together, you have a normal form. So it turns out any complex vector of dimension that lives in the C d to the m can be expressed in this form. So if you had this vector, you can kind of express it as a ZXW diagram by putting all the entries on these green boxes. And then essentially these wires carrying the multipliers connecting to the X spiders. There's m of these X spiders, and then there's like loads of these multipliers, and the multipliers essentially encode the D array representation of that number. So if you have the ith entry, this is the D array, instead of binary representation. So each wire carries a digit. Yeah. Anyway, so it's easy to see how this works. Hopefully. So now onto the actual main completeness proof. So there's this thing called map state duality, which is very useful in quantum computing. You can take any quantum map, linear map, and you can kind of bend it around. It's a bit like currying. You apply a cap on it and bend all the input wires into output wires. Yes, because we're reading downwards. So these maps and states are equivalent. So we're gonna, to show completeness on all ZX diagrams, we're gonna focus on the states. So we bend everything around. And now the goal is for any of these states, we can always write these states. There's a procedure to write these states into a normal form. And because these rewrite rules are reversible, there's always that completes your path. You can go this way and go this way. There's a path to go all the way from D1 to D2. And then you bend everything up, and it's fine. Yeah, and if you look inside one of these D1s, you can pick some foliation of these diagrams so that you can cut them out into layers, where each layer consists of like a tensor product of these generators. Yeah. And so like we can start working our way down. If you look at A1 here, we're going to start turning it into a normal form. That can be done inductively. So we open N1 into what happened? Yeah, into these generators, and we perform the tensor product. I'll get back to that. When you have A1, you turn it to normal form, and then you compose it with A2, and then you're going to bend it around with the snake equation. And now you see this thing is another state with the map state duality. So there is a way to turn it into a normal form. So we do that. And then we're going to do the tensor product. And then if you can show that the tensor product of two normal forms can be rewritten into a single normal form, then that's good, right? That's one of the steps. And then a step after that is if you have a single normal form, you can then perform the partial trace of this normal form. And if you can show the partial trace of a normal form is still a normal form, then that's good. You can proceed inductively. So if you keep doing this, you're gonna kind of compress everything into a single normal form. And you do that on both sides, you're gonna get the same normal form because they have the same interpretation, right? So that completes the completeness proof at the high level. In summary, we're going to turn every generator into a normal form by reading out its entries. We're going to do that as the base case of induction. And then as part of this kind of weird induction proof, you're going to show the tensor product of two normal forms is a normal form. And you're going to show the partial trace of a normal form is still a normal form. So this is one of the base cases. You take the Z spider with no input wires because we can bend everything down. We have flex symmetry in the Z box. That's good. And this, you've seen earlier this definition of the Z box. So those are the entries of that vector. So we're happy with that. And like once again, you can see the wires. You can see because one is at the 0th entry. So this theory representation is 0, 0, 0. So there's no cables. At the end, is everything's d minus 1, d minus 1, d minus 1. So minus d minus 1 is 1 modulo d. So that's why you have that. And then for the W node, once again, we apply map state duality. And with enough work, you can also turn this thing into this thing, which ironically has another W in it, but that's okay. This is important in the proof. So you can do that also for the W spider. And yeah, you can also do it for the Hadamard. And in qubits, the Hadamard effectively maps, instead of mapping the computational basis state to the Hadamard state, instead of mapping to the computational basis to the Hadamard basis, this generalizes from mapping the computational basis to kind of like the Fourier basis for high dimensions. So that's why you see all these roots of unity flying around. If you look at the entries, it forms a like Fourier transform. So yeah, that's the statement that you can tensor two normal forms into one. The proof's a bit long, so it's not going to be on the slides, but you can read through it in the paper. It's just using the rules that we've developed. Yeah. The partial trace once again. So you can see this wire here between S and T. When you do the partial trace, you still get another normal form, but with some of the entries kind of summed together on the green boxes you see above. We're effectively simulating tensor network contraction. So it's a pretty blunt proof. But if you look at some of these Clifford proofs, they involve like actual quantum-y aspects of the proof. But here is actually a statement about arbitrary linear maps, not just quantum states. Yeah. Yeah. So that was another, like, we zoomed into this high-level proof, and now I have lots of time, so I can painfully walk you through the rules of the ZXW calculus. So you have fusion. So if you fuse these Z boxes together, instead of adding the phases, I already said this, you can do element-wise multiplication of the things. And these Frobenius algebras, they're symmetric, so you can swap the wires. It doesn't matter. Thankfully, you still have these two-legged versions being identities, so that's good. You have this thing called D. It's kind of like dualizer, so when you pass it through the green box, it's very small, but you can see the arrow gets reversed, so the order of these coefficients gets reversed. And D kind of appears when you bend down the pink spider, because the pink spider is not flex symmetric. But it does have fusion, this was a conscious choice we made. We can choose between having fusion, normal fusion, or flex symmetry, and we decided fusion was better. Yeah, once again, you have the bioalgebra, and this is kind of obvious. If you remember that this box, the first coefficient is 1 always. The 1 was here, but we don't write it down. So when you plug it in with ket 0, it becomes 1. So the empty diagram is 1, right? That's the monodal unit. The Z spider still copies computational basis states, so that's good. And these generalized Paulis also copy through, so that's good. This is the generalization of the kind of pi copy that turns alpha into minus alpha, but except here we're working with Z-box, and it's a d-dimensional Z-box, so now you need to like do the reciprocal of everything. Yep, this is straight from reading our definitions of things. They're pretty straightforward. Another thing we have is the Hadamard gate is not involutive in higher dimensions. You need to apply 4 of them. So yeah, h to the 4 is the identity. So you have h squared equals this d thing, this dualizer. But thankfully, d is involutive, so it stops at 4 for all dimensions. And then here's the ZW fragment of the rules. So you have the W spider, and there's a way to think about the W spiders as kind of adding these green boxes act as a monoid. So that's written that way around, but this can also be written the same way around. So if you have A and B plugged in, it adds them element-wise. And if you think of these boxes, it's performing multiplication element-wise on these boxes. So that's just saying like you can factorize, you know, if you have x times a plus b, have xa plus a xb, you know, this is very natural to reason with these things on the basis state level, but it can express everything in its superposition as well. The W spider is symmetric, and the W spider is associative, which is good. It has the bioalgebra, which I said earlier, and in fact, the W spider has a bioalgebra with itself, but that only holds when you project it into the single particle subspace once again. And if you remove this projector, you still have it. It still works, but these swaps, all the swaps in the N case, has to be replaced with fermionic swaps. But since there's only one particle, you don't need a fermionic swap because there's nothing to interact with. And here's some more rules. I think I can try to provide some intuition. So once again, that's the definition of the W state. Copies as get 0. This thing underneath is a bit weird. My intuition is I think, remember when you plug in the non-zero state, you're going to get a sum of these k's. You can get like k1, but in all possible positions. I think this is like post-selecting on exactly one of the terms. That's my intuition, but I might be wrong. This is a trialgebra rule, once again. This is using the single particle subspace trick, which is useful, it turns out. And then finally, here's a lot of really crazy rules we had to develop. This is the bulk of the work, so I thank my co-authors for working this out. This is how we turn the Hadamard into, this rule here is really important for turning Hadamard into the normal form. And without that, we wouldn't have the high dimensional proof for ZXW, completeness of ZXW. So in summary, outlook, yes. This italicized thing, that's already been done by some of my co-authors. They use the ZXW calculus to do photonics, which is really cool. Photonic reasoning, computation. So completeness now tells us it's always possible to do this rewriting from one equivalent diagram to another. Now we need to find efficient procedures to do this all the time. Well, maybe not all the time, because that would collapse a few like complexity hierarchies, and then we wouldn't need quantum computers anymore. So we'll try to make it better, and we want to generalize this to a Q-finite ZXW calculus where the Ys can each carry different dimensions, which will be quite interesting. And then finally, like we can focus on specific case of compilation, so we can encode Hamiltonians easily in ZXW calculus. Maybe we can use it to do some good compilation with chemistry as well. So yeah, this is the appendix. It's a bunch of stuff. This is the flex symmetry thing I was talking about. Here's how these boxes are defined. It's just syntactic sugar, and these are the references. So thank you.
All right, thank you. All right, are there any questions? All right, let's start with the in-person one. Yes.
Hi, thanks. Can you do, or have you thought about doing a circuit extraction as part of the optimization with
What structure, sorry?
circuit extraction?
Yes.
Yeah.
So yeah, as you know, as many of you know, the circuit extraction problem in general is quite hard. Let me find some ZXW diagrams. So these are not circuits. You can code your problems into these diagrams, and this is obviously not a circuit. But to run a quantum computer, you need to turn into a quantum circuit, and there's a gap between encoding a problem with these diagrams and turn into actual something that can be run on a quantum machine. And in general, this is known to be hard for very similar calculi, so we expect this to be the same. But we hope to work with some fragments where it's easy to extract. That's normally the trick. We work with these gadgets that can be extracted. Another trick is if we don't send it to a quantum computer, we can do like stabilizer decompositions. You can take these non-unitary bits and like express them as sum of stabilizers. And by the Gauss-Knill theorem, you can simulate these things efficiently. So that's one way to like compete with like tensor network contraction, tensor network simulations. So that's something that came out recently. There's a paper you can look online about that. So there's lots of ways to get around circuit extraction, but I suspect in general it's still going to be a hard problem.
Okay, yeah, thanks.
Thank you.
Right, any more questions? Seems like not in person. All right, are there any questions from the online participants? Okay, it seems also no, so let's thank our speaker again. All right, and we will resume with the next talk in 2 minutes.